The second part of the notes today are about gas laws variables. And gas laws variables are the things that can change within the parameters of the gas laws. Okay, we have some actual laws that pertain to gases, and we're going to talk about those later. But before we talk about those, we have to talk about the different parts of the gas laws. The first variable we're going to talk about is mass. Gases have mass. You might think that a gas is weightless, like it doesn't have any mass, but because they are classified as matter, and matter is something that we says has volume and has mass, we say that gases also have mass. Okay, remember that masses are measured in grams or kilograms. Okay, the density of a gas is much less than the density of a liquid or a solid. Remember, the density is how much mass you have in a specific space. We call it the mass per unit of volume. So if something is really dense, there's a lot of particles in a little area. If something is less dense, there's less particles in that area as well. Okay. Now, so a density of a gas is going to be much less than a liquid or a solid. And that makes sense because if you think about a liquid or a solid, the particles are much closer together in a liquid or a solid, whereas a gas, the particles are much further apart. The density is so low, and that's what allows us to be able to walk through a room without worrying about battling through air. If there were a lot of particles, it would kind of feel like you were battling the wind because like you'd be walking into a lot of particles that are in the way. Think about walking through in water. If you're trying to walk in water, like across a pool, it's a lot harder than walking in air. So water is more dense, so it's harder for you to walk through. Same thing if like you were walking through mud, something like that. It's got more density, so there's more particles for you to walk through. Since it is so easy to swim across the room, we don't really think about the mass of the gas that's in a room. And it's only noticeable if we have a large collection of gas in a container. You may have seen oxygen containers or helium containers. That's when we notice the mass of the gas because we have a collection of all of the same kind of gas in a specific container. So this is a graphic that can has led to the belief that gases have a mass. If we weigh a basketball and it's deflated, we have a certain weight. Okay, that could be anything, any number you can think of. It could be 20. Okay, but when we inflate the ball, you notice what has happened to the scale. The scale has increased. We haven't changed the ball at all, so the only conclusion is that the gas that we have put into the ball must have some sort of mass. It must have some grams. So that's our conclusion. We can base that based on the observations of seeing that when the ball is deflated, it has a lower mass than when it is inflated. So when we talk about the mass of a gas, we assume that the gases are composed of a collection of particles. There's a bunch of particles together. You can't see any of the particles, and to notice any mass, you have to weigh a collection of the particles. You can't just weigh one particle of oxygen or one particle of helium. It's just too tiny, it's not going to be possible. So you have to have a collection of them, okay? We usually need a mole or more. Remember that a mole is 6.02 times 10 to the 23rd particles. So we would need at least a mole of those gas particles to have a significant change in mass. So we would need that many. Remember, that's a really, really big number. So that's a lot of gas we would need. The second variable we're going to talk about is gases are squeezable. Okay, so what that means is that if you squeeze a gas, you can actually reduce the volume. And if you look at the picture here, you can see it. There's a lot of empty space in between the particles. When we push down over here, you can see that the volume has changed. So we've gone from a volume of this big down to a volume of down here. So you can see the size, obviously it's been reduced a a lot. So this is because of the density. There's a lot of empty space between those gas particles, and you can see that. The blue dots are your gas particles, and in between there's white space. Over here, in this one, you can't really see a lot of white space, but you see more blue, so the particles are more compressed together. Gas particles have a very high velocity, so even though they're very small, they move extremely fast. Okay, velocity is similar to speed. Okay, because they're moving at a high speed or a high velocity, they have a lot of energy, and when something is moving very fast, it has a lot of movement. What happens is that because they're moving so quickly and they have a lot of energy, the movement causes the gases to spread out, so they want to have more space. The empty space that's there, like the white space in the previous picture, the empty space can be compressed, which allows the gas particles to have less room to move around. So the pressure, okay, we can increase, which is going to decrease the volume, the amount of space that the particles are taking up. Gases fill their containers, and that's another variable that we deal with, okay? They're going to expand, gases will expand until they take up as much room as they possibly can. If you think about a balloon, if you blow air into it, it's going to expand until finally the balloon can't withstand the pressure anymore, the gas, and it pops. Gases will spread out to fill containers until the concentration is uniform throughout. So for example, if we have a container here, the particles don't all want to be down here. They want to spread out. So they would fill the container and make it as evenly spread out as possible. So until it's uniform, the space between. This is why that there's never an absence of air around you. You can always breathe. You don't have to walk to one part of the room to breathe because that's where all the air is. The air keeps spreading out and fills the room that it's in. This diagram shows you the different states of matter and how the particles look within those states of matter. These are oxygen molecules, so these are O2. You can see that there's two little circles next to each other. Each one of them is representing an oxygen, and we know that oxygen is diatomic, so it is always traveling in pairs, and that's what all of these are. If you take a look, you can see that the gas molecules, which is in the big part here, okay, they're nice and spread out, and there's a lot of white space in between them. If we look down here at the liquid, you can see that the liquid, okay, which this could be representing water, right, 1 oxygen, 2 hydrogens, you can see that the liquid, they have a little bit of less white space between them. The particles are a lot closer together. And then if you look over here at a solid, the solid, you can't see any white space in this area at all. So that means that the particles are much closer together in the solid. Gases diffuse. You learned about diffusion before in biology, and we talked a little bit about it, but we're going to talk about it even more. Okay, diffusion just means that it's moving from one substance, or it's moving from one place to another. Okay, gases can move through each other quickly, very, very rapidly. The movement of one substance through another is called diffusion. Diffusion always goes from higher concentration to lower concentration. Again, this is why if you spray perfume in one end of the room, okay, it'll start to spread out through what we call diffusion, from an area of high concentration where there's a lot of perfume particles to areas where there's not as much. Gases are always colliding with each other. The particles are always colliding with each other and with any objects that are in their path. So they exert pressure. They put pressure on the objects in their path. What happens is we can add up, we can take the sum of all the collisions, and that makes up the pressure. So the more collisions that are happening, so here's a collision, this is colliding with the outside of the box here, this is colliding. So the more collisions there are with the outside of the box, the more pressure the gas is going to exert on the box. Pressure depends on temperature, and I talked a little bit about that in the last video. The higher the temperature of a gas, the higher the pressure of the gas. So as we increase the temperature, you're going to increase the pressure that the gas exerts. The reverse of that is true as well. So if we decrease the pressure, we will also decrease the temperature too. Here's just a diagram for you to see. If the temperature today was 35 degrees Fahrenheit, that's fairly cold. You can see that the pressure gauge is fairly low. If the temperature increases to 85 degrees, what have you noticed? The pressure gauge is now higher. So it was over here, when it was a lower temperature, the pressure now has gone up to a higher pressure. If when you guys start driving cars, or if somebody you know has a car, sometimes when the air gets cold, their tire light will go on saying that they have low pressure. In order to measure gas variables, you need different values. The first thing you need is the amount of the gas, the volume of the gas, the temperature of the gas, and the pressure of the gas. These are the 4 variables that we deal with the most. Amount is abbreviated by the letter N, and it is expressed in moles of gas. So remember, I told you that moles was not going to go away. So when we talk about the amount of a gas, we're going to say there's 3 moles, 4 moles, whatever. When we talk about moles, we know that that is 6.02 times 10 to the 23rd molecules of that gas. So you could have 4 moles, 5 moles of oxygen, 6 moles of oxygen, whatever. That's telling you the amount or how much gas you have. Volume, we represent volume with a capital V. That's going to equal the volume of the container. So when we talk about volume, we talk about liters, okay? Sometimes we use cubic meters or decimeters cubed, which is dm cubed here, which is also equal to 1 liter. Temperature is a pretty easy variable. It's represented with a capital T. The temperature of a gas is measured with a thermometer, and it's measured in Celsius. When we talk about gases, calculations have to be done in the SI unit, and the SI unit is what we call Kelvin. And we did temperature conversions a very long time ago, and we're going to bring those back. This is the equation in order to figure out Kelvin. So if you have, 10 degrees Celsius, you're going to add 273 to that, and you would end up with 283 Kelvin, and we abbreviate Kelvin with a K. Pressure is another variable that we deal with, and that's how much force is exerted on the wall of the container that's holding the gas. We use the letter P to abbreviate that, and we have a bunch of units for pressure. So you're going to have to be able to convert between these units. We have the first one that's called atmospheres, which are abbreviated as ATM. We have millimeters of mercury. Okay, this is called abbreviated with mmHg, millimeters, and then the abbreviation for mercury. And then we have kilopascals and pascals, so you have to be able to convert between pascals and kilopascals. You'll have to remember that there are 1,000 pascals in 1 kilopascal. In order to convert pressure, or convert P, you most of the time want to get it into pascals. So you'll have to convert the given unit to pascals and then to the wanted unit. We'll be doing some practice with that, but make sure you get that in your notes to start. The last part of variables is talking about what we call STP. And STP is what we say are standard conditions. They're the normal conditions. So the behavior of the gas depends on the temperature and the pressure where the gas is held. When we talk about the behavior of a gas, we usually talk about standard conditions, the normal conditions that we have, and that's called STP. It stands for standard temperature and pressure, the normal temperature and the normal pressure. For temperature, the standard condition is 0 degrees Celsius or 273 K. For pressure, it's either 1 atm, 760 millimeters of mercury, or 101.3 kPa. And that's it for your notes. Make sure you get the worksheet from Ms. Heinz and finish that off.